Hello, everyone. I hope everybody's doing okay out there. We are moving on to our next section of Chapter 18, which is called Chemical Equilibrium. Okay. To understand chemical equilibrium, we first have to look at a reversible reaction. Okay. A reversible reaction, as it says, is a reaction in which the conversion of reactants to products and the conversion of products to reactants happens simultaneously. If we think about chemical reactions that we have been talking about all year, we've only turned reactants into products. Basically, we assume that all reactions went to completion, meaning as much reactants as could react did react. In principle, though, every chemical reaction is reversible. If we look at the example here, and let's get a highlighter out here, or a laser pointer. We have SO2 reacting with oxygen to form SO3. But what also happens is if we have just SO3, it can decompose into SO2 and O2. So we get this reversible reaction as designated by this double arrow. Okay. And I said in principle all chemical reactions are reversible, but many are not. Right? If we think about like explosions or even just burning a piece of paper, you can't really make that reversible. But in the world of chemistry, many reactions are reversible. So if we look at what equilibrium means, right? We have this reaction. Right now, we're not showing it as equilibrium, but this will eventually be an equilibrium reaction. So if we start with just N2O4, which is a colorless liquid in this tube, right? It's naturally going to produce some NO2, which is brown. Okay? So here in this picture, we have only N2O4 molecules. As we start making some product, we see here that there's an NO2 and an NO2. Okay. Eventually, what is going to happen is these NO2 will start reacting to form N2O4. And so at some point, we'll kind of see, and it's hard to like count in this picture, but we'll get to a point where these numbers of molecules aren't changing and the color will stay this same brownish color. It won't turn all of the N2O4 into NO2. It will only turn some of it. Change the slide here. Okay. And if we look, right, we still have the tubes here as they're getting brown of the same picture, but now we're graphing the concentration. Right? Remember we started with just N2O4, which was colorless, and no NO2. Over time, the concentration of the N2O4 is going to go down. The concentration of the NO2 is going to increase, and we see right about here, they remain constant. Okay? And so that leads us to our definition of chemical equilibrium, which is the point at which the rate of the forward reaction is equal to the rate of the reverse reaction. Here we see we have the rate over time. And so this forward reaction, because we only started with NO2, is going to slow down. Okay? The reverse reaction starts at 0 because there is no NO2. And if we think back from our last reaction rates section of chapter 18, the higher the concentration, the faster the rate. So this is going to be fastest at the beginning and slow down. This is going to be slowest at the beginning because there is no NO2. It's going to speed up until the point at which the forward rate, the rate that the N2O4 is producing NO2, is equal to the rate that the NO2 is producing N2O4. So notice the two different graphs. This is concentration over time. Okay. The concentrations do not have to be equal. And in fact, they typically will not be equal. They could be, but almost never are. Whereas in the rate versus time, the rates are always going to come to be equal at equilibrium. That is our definition, when the forward and reverse reaction rates are equal, which also leads to the concentrations not changing over time. On this graph, it is similar to what we had in the other two graphs, just a slightly different presentation. Here is our concentration over time. And you see in this one, we start with an actual amount of N2O4 and again 0 NO2. And you'll see we reach at this dashed line the point where those concentrations aren't changing. Okay. This would be called actually an equilibrium point. Okay. This point, these concentrations aren't going to always be the same. Okay. We though can reach the same point, and the math there is something beyond where we'll be. But if you started with 0.08 of the NO2 and 0 of the N2O4, you're actually going to come to the same equilibrium point. And you'll notice that that's 0.04, that's 0.08. This is a 1 to 2 ratio. Again, we're not going to get into that math, but in case you're curious. Now, if we started with like 0.06 of the NO2, we're not going to come to the same equilibrium point. We'll have some other values. Again, for us, that is actually a little bit beyond our scope of calculating what those values would be. But it's just, we always want to get the key point is that they're not always going to come to the same final concentration. It depends upon how much you start with. And you could start with a mixture of both of them. Okay. Now, note, we're still going to call everything on the left of the chemical equation reactant and everything on the right products. So even though in this right-hand graph we start with NO2 only and no N2O4, just by convention, the way we do things, we're still going to call NO2 the product and N2O4 the reactant, because that's how we have it written on the graph. Okay. And so kind of put some words to this. If we look at just a very generic, with A being our reactants, B being our products, assuming we start only with A is going to decrease until it reaches a constant rate. B is going to increase until it's a constant rate, and therefore the forward and reverse reaction rates will be equal. And again, the concentrations or amount, the reactants, are going to go down until they plateau off. The product's going to increase until they plateau off, and we see at equilibrium the concentrations don't change. Okay. The other thing is, as we saw in the previous graph, these lines might cross, they might not cross. They don't have to cross, right? So it really actually all depends upon how much you start with and actually the coefficients in your equation and all of that good stuff.
Have you seen Junior's grades?